Multi-agent systems have rapidly become the standard for tackling complex reasoning tasks with large language models. But there is a fundamental bottleneck in how we currently design these systems. Most multi-agent architectures rely on static, predefined communication topologies. You design a graph, you hardcode the workflow, and then you compile it. This design-then-compile paradigm works for specific tasks, but it lacks elasticity. When the reasoning process encounters a dynamic shift or a subproblem that requires a different collaboration pattern, the system is stuck. It either overcommutes resources or fails to adapt. This paper introduces differentiable mixture of agents, or DMoA, a framework that eliminates this rigidity. DMoA enables self-evolving, elastic collaboration by introducing a differentiable routing mechanism that dynamically selects and activates agents at every reasoning step. It treats agent routing analogously to mixture of experts in neural networks, but applies it at the reasoning level rather than the token level. The result is a system that can implicitly simulate arbitrary communication topologies, adapt to evolving demands, and optimize itself using self-supervised signals without external annotations. Let's break down the architecture and the technical mechanisms that make this possible. In DMoA, the system operates over a predefined agent pool. An agent is defined as a runtime concept comprising a base LLM instance, a profile that activates specific capabilities via system prompts, and a set of external tools. Unlike graph-based approaches where the number of agents and edges are fixed, DMoA maintains a pool of candidate agents and adaptively selects a subset at each reasoning step. This allows the number of active agents to vary, providing spatio-temporal flexibility. The core innovation is the differentiable routing mechanism. At each reasoning step, the router must decide which agents to activate based on the current context and the history of previous decisions. To achieve this, DMoA employs a lightweight routing module consisting of a sentence transformer and a recurrent neural network. The process begins by encoding the user query into a semantic vector using the sentence transformer. This vector serves as the initial context. The router then uses an RNN, specifically a GRU, to maintain a hidden state that captures historical routing information. This recurrent structure is crucial because it allows the system to carry forward context across reasoning steps, enabling the construction of cross-step communication patterns and supporting autoregressive extension during inference. Mathematically, at step I, the router takes the current semantic context xi and the previous hidden state hi1 to produce logits zi over the entire agent pool. The context xi is updated by aggregating the semantic embeddings of the responses from the previous step, weighted by the routing probabilities. This ensures the router is sensitive to the magnitude and content of the information generated by the agents. The routing decision is sparse and adaptive. DMoA does not use a fixed number of agents per step. Instead, it determines the number of rooted agents, ki, dynamically. The selection rule ensures that only agents with normalized weights above the average value and within the top k candidates are activated. This is controlled by a temperature coefficient tau and a hyperparameter k, allowing the system to tune routing sensitivity and sparsity. This mechanism ensures that DMoA can route anywhere from a single expert to a collaborative ensemble, depending on the complexity of the step. Now let's look at how DMoA is optimized. This is where the approach diverges significantly from other self-evolving multi-agent systems. Many existing methods rely on reinforcement learning to optimize topology designers. RL suffers from sparse reward signals and requires extensive rollout episodes, which hinders convergence and prevents zero-shot generalization. DMoA avoids this by introducing predictive entropy as a self-supervised optimization signal. The hypothesis is that the routing mechanism should select agents that exhibit high confidence in their predictions. Predictive entropy is a well-established metric for evaluating model confidence. For an agent generating a sequence of tokens, the predictive entropy is the average conditional entropy over the output distribution. Lower entropy indicates higher confidence. During optimization, DMoA runs all candidate agents in a reasoning step to collect their predictive entropy vectors. These entropy values are converted into confidence targets using a softmax over the negative entropy. The router is then trained using a pairwise ranking loss to align the routing probabilities with these confidence targets. This loss function encourages the router to assign higher probabilities to agents with lower entropy, effectively learning to route to the most confident experts for the current context. This self-supervised paradigm offers two major advantages. First, the supervision signal is dense and available at every step, providing strong gradient flow for the differentiable router. Second, it supports test-time training. Since the entropy signal can be collected during inference without ground truth labels, DMoA can adapt to unseen tasks on the fly. In practice, you can process a small batch of test queries in a dense mode to collect entropy signals, update the router via the ranking loss, and then switch back to sparse activation for the remaining queries. This enables lifelong adaptation without retraining the underlying LLMs. The inference process leverages this trained router to perform sparse activation. At each step, the router computes logits, selects the top ki agents, and executes only those agents. The responses are aggregated to form the context for the next step. A summarizer agent can be employed to organize the final output, or to autonomously determine when the reasoning process should terminate based on the sufficiency of the evidence. The experimental results validate the effectiveness of this approach. DMoA was evaluated across 9 benchmarks spanning mathematical reasoning, code generation, web-based question answering, and medical diagnosis. Using a unified backbone model, DMoA achieves state-of-the-art performance compared to single-agent methods, static multi-agent systems, and other self-evolving approaches. The improvements are particularly pronounced on complex tasks, demonstrating the router's ability to dynamically tune communication and schedule resources effectively. Beyond accuracy, DMoA exhibits superior efficiency. By activating only the necessary agents at each step, DMoA consumes significantly fewer tokens than graph-based baselines while maintaining higher accuracy. This confirms that the differentiable routing successfully identifies and leverages specialized agents only when they are truly needed, avoiding the token bloat associated with fully connected or redundant workflows. Robustness is another key strength. In adversarial settings where a subset of agents is compromised, DMoA maintains performance stability. The adaptive topology mechanism allows the system to bypass unreliable agents and rely on the ensemble of robust experts, showing resilience that static topologies lack. Scalability analysis reveals that DMoA benefits from increasing the size of the agent pool and the maximum routing budget. As the pool grows, the system can access a more diverse set of capabilities, and the router learns to utilize this diversity effectively, though with diminishing marginal gains. This suggests that DMoA can scale to support richer agent ecosystems. In summary, differentiable mixture of agents represents a significant step forward in multi-agent reasoning. By replacing rigid, precompiled topologies with a differentiable, context-aware routing mechanism, DMoA enables elastic and adaptive collaboration. The use of predictive entropy for self-supervised optimization removes the dependency on external labels and unlocks test-time adaptation. This framework not only improves performance and efficiency, but also provides a pathway towards self-evolving swarm intelligence that can dynamically reconfigure itself to meet the demands of complex, evolving tasks.